Hi, my name is Oscar de Groot. I'm a PhD student at the Cognitive Robotics department of the TU Delft. And I'm here today to talk about our work on scenario-based trajectory optimization in uncertain dynamic environments. The motivation for this work is that motion planning algorithms often have a safety-critical collision avoidance constraint with respect to obstacles in the workspace. But when these obstacles move, then they have a motion which is not exactly known to us. And so any safe algorithm needs to consider the uncertainty when they try to satisfy the safety-critical collision avoidance constraint. Now, an example of where these methods could be useful is in urban driving, where, for example, in this intersection, in order for us to drive from the left to the right, we need to be aware of the uncertainty associated with the trajectories of the obstacles in the workspace. And that's the actual goal statement of this work, is to look at motion planning under obstacle uncertainty while still providing safety guarantees. Now, this motion planning algorithm has to be smooth in real time so that we can actuate an actual robot with this. And the obstacle uncertainty can be non-Gaussian and unbounded. And especially the non-Gaussian part is interesting because these trajectories of obstacles tend to be multimodal. For example, we cannot be sure that a pedestrian will walk straight or will turn right at the next intersection, and we have to be able to encode this into our uncertainty. Now, the safety guarantees are with respect to collision avoidance, and because the obstacle position is uncertain, this will turn out to be probabilistic. Before moving on to the details of our method, I would first like to briefly introduce the state of the art on the field of planning under uncertainty. And the main trade-off that we find ourselves in is that we have to approximate the risk region that we need to stay out of because it cannot be computed in real time. And at the same time, we want this approximation to be safe, but not too conservative. So it has to be not much bigger than the original region. Now, in the Gaussian case, there are good solutions. One solution is to look at the distribution and find the level sets. And these level sets tend to be ellipsoidal. And so the ellipsoids can be computed exactly and can be used in computation. And this tends to be quite conservative, but is a simple method. On the other hand, one approach that's very tight is to use linearized collision regions and to evaluate then in 1D the cumulative density function, which we have an expression for. And that's the second approach, which we see also visualized in this figure, where we have a Gaussian distribution in the center. And we did a Monte Carlo evaluation of the actual risk region. And what we see is that the second approach, or this linear approach, actually overlaps almost with this risk region. So this is quite a good approximation. Now, in the non-Gaussian case, we have this moment-based approach, which propagates the stochastic moments of the distribution through the constraints. And this is something that's visualized in the right figure, where we have a Gaussian mixture model in the center, which is non-Gaussian. And in red, we see this Monte Carlo evaluation of the region again, that is safe. And this method 3 is illustrated in black, which is a more conservative approximation, but it's quite consistent. Now, the approach that I will present today is a scenario model predictive contouring control approach, or SMPCC, which is an empirical approximation of the chance constraint. And we see in this right figure, the yellow region corresponds to this method. And it turns out that this is much less conservative than this black approach. And we show how we can use this approach in motion planning algorithms. We will consider the following problem formulation, where we have a vehicle with nonlinear discretized dynamics, and dynamic obstacles that have an uncertain position at time step k, which you note by delta k in this delta of k, which is the probability space. And this delta k distributes according to p of k, which is a probability density function. We assume to be non-Gaussian and unbounded. But we restrict ourselves to the marginal case, where probability at time k is independent of the probability at time k plus 1. In this setting, we formulate a chance constraint model predictive control problem, where we have an objective that specifies if we want to make progress towards our goal. We have our dynamics, and we have chance constraints on the collision avoidance. Inside of the probability, you have a collision avoidance constraint that ensures that the disks modeling the vehicle region and a disk modeling the obstacle region do not overlap. And since this is specified in probability, we want this to hold with a probability of at least 1 minus epsilon k, where epsilon k is a level of acceptable risk. And we note that this constraint is specified for each stage k in the optimization. We will now show how we solve this chance constraint model predictive control problem by safely approximating the chance constraint. And this is what we refer to as a scenario model predictive contouring control approach. Now, the first step in our approach is to locally linearize the collision constraints, and this process is visualized here on the slide. where we move from this left distribution to the right distribution, which was linearized with respect to the first vehicle disk. And we get a smeared out distribution that is still locally accurate. And the motivation for this is that it significantly simplifies the optimization, especially when sampled. And since we repeatedly solve the motion planning problem, it's sufficient to be locally accurate because the solution will not shift a lot between stages. So to move to this empirical approximation of the problem, we make use of scenario optimization. Where the main idea in scenario optimization is that we have this chance constraint problem, which specifies some constraint in an uncertainty. This uncertainty is denoted by delta. And from this delta, the approach is that we draw S samples from our distribution, which in our case we could think of as obstacle positions. And for each of these positions that we drew, we specify a new constraint that is deterministic. But in total, we have a large set of samples now. And this so-called scenario program is then an empirical approximation of the problem. And so this moves this uncertain problem to an empirical approximation, where each scenario that we originally drew generates a half space for the new problem. And the question is, of course, how well does the empirical solution now give guarantees on the original problem? Now, to find the result in this direction, we look again at the scenario optimization approach. And specifically, we have to look at the support subsample, which is the set of samples that if we optimize with respect to these samples, then the solution is the same as with all the samples in place. And that means that this is a small subset of all the samples that we can use as an indicator to find the risk of the optimization. Now, if we define the violation probability as the probability of drawing a realization where the constraint is violated, then this is more or less the risk that we experience of our constraint. And it turns out that the probability that this violation probability is bigger than the risk that we specify is upper bounded by some beta. Now, the main factors in this equation are the support that we found, the sample size that we use to draw the samples, and also the level of risk that we would like to achieve. And so this equation gives a full relation between the actual optimization that we solved and the initial sample size and risk that we need. Now, the key observation that makes our approach efficient is that the scenario program has been constructed from the set of half spaces, as is visualized on the left here. It has a lot of redundant constraints. In fact, it can be reduced to the problem on the right, where only the intersection of the half spaces is used as a constraint for the vehicle. Now, additionally, since these constraints that are in the intersection are the only ones that can influence the vehicle, we directly gain an estimate of the support subsample. So in this right case, the support subsample would simply be 3, and we can use it directly to find the risk of the optimization. So to conclude our approach, this is how we move from this complicated chance constraint problem to an empirical approximation, while our empirical approximation is able to provide safety guarantees on the original problem. In the following, we'll show a set of simulations that show how our method performs in practice. Following simulations, we've used these parameters, where we have a sample size of more than 50,000 samples, a risk of 1.1%, and a beta probability of 10 to the minus 6th, where if you recall, this was the probability that the empirical approximation is infeasible for the original chance constraint problem. And we see that this probability is very small. Now in the next videos, we will see the robot visualized in black and its trajectory that we optimize shown in blue. Now from the top and the bottom of the video, we'll see pedestrians crossing the road, and their predictions are visualized with this pink color. Now for 3 of the stages, we will show what the scenario approach is doing in these red, orange, and yellow colors. On the one hand, we'll see the scenarios denoted with black dots, and in colored dots, we'll see the scenarios that are in the support subsample. Then additionally, we'll also show the regions that result from the intersection of the half spaces, and these are also colored. Now it's important to denote that the actual pedestrians are shown in red. And so here is a comparison between a scenario model predictive contouring controller and a baseline model predictive contouring controller approach with the level sets of the Gaussian functions. And we can see that the scenario approach is able to find much better smooth trajectories through space and seems to plan better ahead, while the model predictive contouring controller struggles to find its way through this complicated environment. We additionally did simulations for non-Gaussian distributions. So in this case, the distributions are radially truncated. And we can see that the robot still finds its way through the space quite efficiently. Now in this other case, we truncated the distribution in the width to indicate that pedestrians are crossing at this section of the road. And what we see is that the robot is moving towards this crossing, stops to wait for a spot where it can move through, and then moves when it's able to. And for the Gaussian case, we did 100 experiments and compared to baseline approaches. And what we saw was that the safety of this scenario-based model predictive contouring controller is better than for the baseline approaches in the sense that the risk is never violated and the average risk is also lower. Additionally, it was able to reach its goal faster than the baselines. And this is something that we saw also in the videos where the smooth trajectories actually led to faster movement through the space. And the cost of this is that the computation times goes up. So this is part of the empirical approximation that takes time to process. But in general, we're stable to run this algorithm at 20 Hz in real time. Now to conclude, we have shown our method allows a robot to find safe motion plans under obstacle uncertainty, and now it's able to accurately estimate the risk in real time. Limitations of our work are partially due to the empirical approximation, which scales poorly to very low risk since the sample size will increase the lower the risk gets. On the other hand, we have also not modeled any interaction between the obstacles and the vehicle, which can be present in practice. This concludes the presentation. Thank you for listening.